Welcome. Welcome to the 38th sort of annual Bunyan Lecture. I'd like to tell you a little bit about this program. This program is the bequest of Mr. James T. Bunyan, who was a Stanford employee of some duration. And he was a man of modest means, but great vision. And as he came towards the later period of his life, he decided he wanted to endow a program that would explore the presence of the development of the universe and the presence of man in the universe. And so he shopped around a bit to various institutions, including Stanford, of course, and very happily for us, through the auspices of our former colleague Ron Bracewell, who in his inimitable way managed to gently, and not very pushily, but humorously encourage Mr. James Bunyan to actually give the bequest to Stanford, and that indeed happened in the end. And because of this, we have now had a wonderful series of lectures. The bequest came in the late 1970s, so I think our first lecture was in Dennis-Chiama in 1979. We've gotten nearly every year. The pandemic and a few other events got in the way of having it completely annually, but this year is our 38th. Now, before we start the lecture, I'd like to just read a few words from Mr. Bunyan's legacy for this event, so you can get some idea what he had in mind. First of all, he explicitly said that part of the visit of the lecture should be to have a public lecture, such as you're getting today, that would be open and free to the public. He very much felt it was important for the upcoming advances in astrophysics and cosmology to be presented to an interested public audience. So those of you who are joining us here at the university, we thank you very much for coming and listening in to this event. He also, as I said, had a very bold and broad vision. Let me read a few comments from what his legacy wanted to be covered. He wanted to have us discuss both original research into the nature of the universe and the origin and destiny of man, and in particular, the structure and working of the cosmos, its galaxies, its stars, and its planets, as well as the dawn of life, the ascent of man, and the status of the human spirit in the scheme of things. This is a pretty broad premise, and of course we have to be able to cover all of it every year, but we've had a number of really distinguished speakers, and it's been really delightful to hear some of the primary researchers of the time, and also people who are good publicizers of science, come and speak to us on these themes. This year's talk is no different. We're very delighted to have Professor Vicki Kaspi join us. And I'll say a few words about Vicki before I let her get started on the lecture itself. First of all, Vicki comes to us from, she's coming from McGill, and there she is if I get the name right, she is the Lorne Trottier, if I can even say it more or less correctly, Professor of Astrophysics.
Close enough.
She has, as all our speakers do to this series, have a number of distinguishing honors and awards. I won't mention too many. She is a member of the Order of Canada and a member of both Royal Philosophical Societies, the Canadian and the British. But given her actual origins in Texas, which she left at a young age, she kindly has agreed to be a member of the a fellow of the American Astronomical Society as well. So with these fellowships, she has certainly distinguished herself in the community, but she's also won many awards. I guess I could mention the Rutherford Prize is pretty distinguished, but she most recently, I think, was actually the Shaw Prize, which she won jointly with Krista Kovaletsu. And that is, I think, for the work somewhat related to what you'll hear about this evening. In addition to these many awards, I want to point out that she has got into this field, the subject that you're going to be hearing about today, the subject of neutron stars and dense matter and the extremes of astrophysics, in a way that I have a connection to. We were both very fortunate to be started off on this path by the eminent Joe Taylor. He's the fellow in the middle of this group with the celebratory beverage and the white shirt. And here is a picture of some of his early students from the 1990s period, I guess. This is taken at an IAU symposium in Sydney. And if you look at me, who is the second person from the edge on the left, you will note it was about 30 odd years ago. Of course, if you look at Vicki, who's the third person on the right, you might be surprised to think that it was more than a few months in the past. Nevertheless, Joe was a wonderful and inspirational person to get when introduced to the excitement of working on these compact objects, which push at the frontiers of physics and allow us, by studying the universe, to learn deep things about the nature of matter and energy and the evolution of the cosmos, as Mr. Bunyan would approve of. Now, Vicki also has followed on very well in Joe's footsteps by assembling a wonderful group of students and postdocs at McGill. This group, they're dynamic, they're diverse, they're dedicated, and they produce some wonderful research, some of which she'll tell you today. I've very happily been able to exchange a few students back and forth with her, so there's some connection with our work here at Stanford as well. But some of the results that this group has put together, I think, will be the subject of today's talk. And so I don't think I'm going to go on any longer, but I thank you very much for joining us, and I hope you'll enjoy this lecture by Vicki Kaspi.
Can we get the lights?
Yes. What was the
We'll bring the lights down a bit so you can enjoy the images on the screen.
lighting? What was the trick here?
Overhead.
Overhead.
There you go.
How's that? And can everybody hear me well? Yes, okay. Well, I just want to say I'm thrilled. Thank you for that very generous intro, and I'm very, very happy to be here and tell you about the fast radio sky. Yeah, there we go. Fast radio sky. My intro slide. And you know, when people ask me nowadays, Vicki, what do you work on? And I say, I don't actually know, because these objects that we're studying, they are a current, interesting astrophysical mystery. And I hope by the end of today's talk, you too will not know what these things are. They're cosmic mysteries of fast radio bursts. And you can see they've also garnered an awful lot of press, a lot of popular press, very mysterious. You'll see them all over the place, these flashes in the night. And you know, they've really captured the imagination. But I want to start with, you know, really what is our perception? What is most people's thought when you think of, you know, the sky? You think of some beautiful, you know, optical image of, I mean, perhaps a famous constellation. I'm sure some of you recognize this as the Orion constellation. And you think, you know, if you look at it tonight, or you look at it, you know, in a week, or in a month, or in 100 years, or in 100,000 years, it's always going to look the same. It's nothing changing. It seems pretty stable. We think of the night sky as something you can rely on and always going to be the same. But of course, that's not true. That's absolutely not true. In fact, 400 years ago, Galileo knew, using even a puny little telescope you could buy for $10 on eBay nowadays, something really crummy, you could look and you can see this is a diagram of the moons of Jupiter. He saw the moons of Jupiter orbiting on an hour time scale, something changing in this supposedly immutable heavens. The sky changes. And this is even, you know, we think of the sun as you know, shining always the same, but no, this is a beautiful movie by NASA's SOHO mission sensitive to the ultraviolet light from the sun. You can see it's rotating and has all sorts of activity on it. Sometimes we have solar flares and coronal mass ejections. We know of all sorts of things in the sky that explode in times that we're not necessarily can predict. This is an example of an explosion on the surface of a white dwarf star that accretes lots of material from a companion star and has a thermonuclear explosion. That's pretty exciting. And we even know of very exotic kinds of explosions that can occur when, for example, two neutron stars, two extremely dense objects, orbit each other, emit gravitational waves, which of course can't be seen, but here are depicted by these sort of blue things coming off, eventually merging and creating a really colossal explosion. So what I'm trying to say is there's lots of things in the sky that are truly transient, that explode, disappear, not so visible immediately to the naked eye, but with telescopes and instruments we detect these things. But of course, I'm here to tell you about the fast radio sky. And to talk a little bit about radio, I have to remind or introduce the young people to this interesting device that perhaps some of you recognize, but isn't really. Let's see, where's my cursor? There it is. So, whoops, I did not mean to do that. Let's go back. Sorry. Yeah, this radio. There we go. So what is a radio? What does this thing do? You all know it has this antenna over here, antenna that's sensitive to radio waves that are traveling through space constantly. And those radio waves hit this antenna and interact with the electrons in it and create a current in that antenna that's then read into some electronic circuits inside the device that amplifies them and converts them, in this case, to sound waves. But this has this really cool features here. There's these dials that can change the frequency of the radio waves that you're detecting. You pick out the radio station that you'd like to listen to with this dial. You turn it, and it adjusts the frequency. And in this case, it's if FM in megahertz. That's a way of measuring frequency, and you can dial and you choose one frequency at a time to listen to. In fact, if you listen to all the frequencies at the same time, that wouldn't sound very good. You'd get a million voices. But that's how a radio works. And of course, radio waves, as you know, are just one part of a vast electromagnetic spectrum of waves that, our eyes, what you're looking at me with right now, are the visible, where our eyes are only sensitive to a tiny portion of that electromagnetic spectrum. That includes, beyond the violet, the ultraviolet, and on the other side of the red, the infrared. Here, the difference in these different colors of light is the wavelength of the light. And so radio waves, the subject, whoops, cool, I pressed that same button, so it has multiple purposes. Okay, I'm learning. I'm just gonna gesture, the Vanna White. So radio waves are on the far end, very long wavelength electromagnetic waves. And that's the subject of the talk today. We're talking about wavelengths that, can be many centimeters, like really macroscopic, something human scale. So fast radio bursts, the phenomenon, so we detect them in radio waves, the same radio waves that your cell phones and TV stations broadcast at. What are they? Well, they're very brief bursts of radio waves that last just a few milliseconds, a few thousandths of a second. They burst and they're gone. And they're happening all over the sky. They're happening right now in this room. We detect them with radio telescopes. That's an example of a radio telescope that's in Parkes, Australia, one where I did my PhD thesis. And you can see this is a very large structure, 64-meter aperture. This is a 3-story building that it's sitting on. You point the telescope to the position in the sky where you want to look. And the radio waves come from outer space, and they bounce off the surface. And the surface is a parabolic, so it focuses it into an antenna that's over here. That's then read out into electronics. It's all, what I'm reminding you of this radio that I showed you, except this one's receiving. The radio waves get turned into electrical currents that go down into the control room and are analyzed, and then we can study them by recording them on a computer. So the first fast radio burst was discovered, in terms of astrophysics fairly recently, in 2007, using this telescope. And the telescope can only see a tiny portion of the sky at any one time, but from the small handful of these bursts that they were detecting, they knew, just from the fact that they could only see a tiny portion of the sky and yet had detected some of them, they knew that the sky rate, if they could look over the full sky all the time, the sky rate was around 1,000 for the entire sky every day. So when the first one was discovered, immediately they knew this was something that wasn't anomalous, it wasn't occasional, it was something ubiquitous in the universe that had never been seen before. And you might ask, why in 2007? It has to do with computers. Computers got fast enough, you could record data at the speeds needed to see just these very, very brief events. As I said, we don't know what they are, and we still don't know what they are. In 2007, it was a shock. Didn't expect this. The one thing we know is that they're not microwave ovens. And you might wonder why I say that. I'm going to explain later. How do we see a fast radio burst? And here's a radio telescope. How do we see it? We definitely do not see it like this. We cannot see radio waves. You know that you can't see them. Otherwise, this room would be you'd hardly be able to see me. How did we see that very first burst? How do we represent it? Taking the electrical currents through the electronics recorded using a computer, and then and digitized in the process. And so this is how we see the burst that was detected with Parkes. This is a graph. You see here on the x-axis, if you see the cursor, you can see my cursor. This is time on the x-axis, but this is just measured in milliseconds, so this is just a half a second of data, 1/2 a second of data. And on the y-axis here is radio frequency. So just like in your radio, you in principle could detect many radio frequencies, but you select one to listen to. Here, using the radio telescope, we receive many of them all at once. And so this is the full, we call it the bandwidth of the radio telescope, going, in this case, not in megahertz, but in gigahertz. From about 1.2 up to 1.5 gigahertz, we see quite a chunk of the radio spectrum. And each point here is a millisecond at that radio frequency. And so you see this horizontal line that is at one fixed frequency at all times. That's a TV station. That's a nuisance to us. We want to chop that garbage out. The astrophysical signal, the burst, is this event here that sweeps through the band, starts at high radio frequencies, and slowly it sweeps through, and, well, I say slowly, but it takes about a few hundred milliseconds, a few fractions of a second, and arrives later at the low radio frequencies. And we call that effect arriving at the high frequency first, dispersion. And I'm going to tell you a lot more about dispersion shortly. But it's that sweep that made the astronomers who detected it, led by this gentleman here, Duncan Lorimer, who's a good friend of mine. And in fact, after him, the first event was called the Lorimer burst. But their jaws hit the floor when they saw this. And they knew instantly this was something truly remarkable. What you're seeing in the inset here is if you correct for the dispersion effect in the computer, so you de-disperse it, that is, you line up, because we believe that dispersion effect is not how the source emitted it. The source emitted all the radio frequencies at once. They got dispersed during their travel to Earth, and I'm going to explain more about that in a moment. But if you correct for this and you line them all back up, that's what you get. You get noise in the radio telescope, and then suddenly a burst, and then nothing but noise. It comes for a few milliseconds, and then it's gone. That's what the fast radio burst looks like. Now, the reason their jaws hit the floor when they saw this plot is because that amount of dispersion is telling us something. It's telling us that this object is coming from billions of light years away. Now, it's not at all obvious. I haven't told you enough yet to understand, but they knew. Billions of light years away. So, and that means far outside the Milky Way galaxy. So we live in a galaxy, a spiral galaxy that looks a lot like this one. In fact, you know this is not the Milky Way galaxy because it's very hard to take a picture of your house, of the inside of your house. It's hard to take a picture of the outside of your house when you're standing inside the house. So we're inside, right in the disk of a Milky Way galaxy. We couldn't possibly get a lovely picture like this, but this is what we think the Milky Way would look like if you could zoom way out and look back. It's a spiral galaxy, and if we could look at at the Milky Way, our solar system is located on the outskirts of this galaxy, roughly here. And we're nowhere near the center of the galaxy, and we think that the fast radio burst is coming from far, far outside our galaxy. And this distance here is about is many tens of thousands of light years. But I'm saying that these things are coming from billions of light years away. And so let's first just take a step and understand, when I say billions of light years away, the farthest reaches of the universe, fast radio bursts are coming from cosmological distances. What does that really mean? Well, you recognize, let's just consider for a moment the scale of the universe. There's the Earth. We're all familiar with the Earth. The Earth is part of a solar system, and zooming out here each time, the last frame is in red. So in the scale of our solar system, where here's the sun, the Earth is, pretty much a speck. But then if you zoom way out of the solar system, the entire solar system in the interstellar neighborhood, just among the closest stars to us, now we're talking about scales of a few light years, the solar system is just a dot. And you can zoom out even further so that the entire interstellar neighborhood is just a tiny dot on the outskirts of a spiral galaxy, and now we're talking about tens of thousands of light years in scale. And then you can zoom way out of the Milky Way galaxy. It turns out the Milky Way is part of the local galactic group. And you see the Milky Way is just a tiny smudge on this scale. That's now, a million light years. And you can zoom further out so that the entire local galactic group now is part of a supercluster of galaxies. And you would zoom way out, and the whole local galactic group is just a smudge there. And you can zoom even further out so that the entire local supercluster is just part of a whole swarm of superclusters of galaxies, so that the whole supercluster is just a smudge. And then if you zoom out to the cosmological scale, that entire supercluster group of cluster of superclusters is really just a spot. And that's now we're talking about billions of light years. And that is the scale that fast radio bursts are coming from. And now you're going to say, well, how do you know that? How do you know that? So let me explain. Let me talk a little bit about dispersion. So I called those radio waves dispersed. You actually know all about dispersion. You're familiar with the phenomenon from the effects. If you've ever seen a rainbow, you're seeing dispersed optical light. White light, like the light from the sun, is actually made up of many colors of the rainbow and can be dispersed by, at least dispersed spatially, by a prism. So that in this case, the white light comes in one direction, but the effect of the matter on those optical waves is frequency dependent. It depends on the wavelength of the light. So red behaves differently inside the prism than does the violet, and it spreads it out spatially. And the same thing's happening here, except it's due to water droplets that are in the sky. But what this so you know about spreading spatially, this spatial dispersion. But what also is happening that's not as obvious is that there's time dispersion as well. So the speed with which those different colors travel in the material when they pass through is different. The red travels at a different speed from the blue. And you might say, but wait a minute, doesn't all light travel at the speed of light? And yes, certainly that's true. That's the cosmic speed limit. Light travels at c, the speed of light. But that's only true in a vacuum. So when light travels in matter, it interacts with that matter, and different frequencies interact differently, and that can cause temporal dispersion. The different frequencies travel at different speeds. And space is not a vacuum. You might, when you look up in the night sky, even with your eyes, actually in some regions, you can see that it's not a vacuum. It's filled with dust, it's filled with plasma and then when electromagnetic waves propagate through that dust and plasma, optical light can get totally blocked, can get scattered. That's what you're seeing here. It's not that there's no stars in these dark regions, it's just that that light has been affected by the dust there. In particular, radio waves are affected by free electrons. And free electrons are everywhere. If you have plasma, that means it's ionized material. There's free electrons there. And in particular, so free electrons are everywhere in the Milky Way. And free electrons disperse radio waves. Just like a prism disperses optical light, just like water disperses optical light, radio waves are dispersed by free electrons. So imagine you have a universe of free electrons, which we do, and you're going to have a burst of radio waves with many different frequencies. You're going to see, as it travels, those radio waves will get dispersed. Different frequencies or wavelengths will travel at different speeds. Whoops. So where's my little video here. So there's your FRB source, and as it travels, the different colors travel at different speeds, so that the higher frequencies arrive before the lower frequencies. In this case, represented by optical colors, of course. I'm talking about radio waves. This is just a way to show them. The blue arrives before the red because of the interaction of those radio waves with the interstellar and intergalactic plasma. Now, I told you the dispersion was telling us that these fast radio bursts are coming from cosmological distances. How do we know that? Well, we know how much plasma, how many free electrons there are in our galaxy. We know how much radio waves can possibly be dispersed if they originated in the Milky Way. So we have maps, actually. We have maps. It's an amazing thing. So if here's a spiral galaxy, this is a model for the distribution, for the density of free electrons in the Milky Way galaxy. The darker shades refer to higher density of free electrons. And this is pretty well calibrated using other astrophysical sources that I could talk your ear off, and I would love to, but another subject, another talk, radio pulsars, where we can measure directly using independent distance estimates and dispersive effects. We can measure the distribution of free electrons in the Milky Way galaxy. And so we have this is actually a contour plot of where each contour, so here's now the galactic, this is looking down on the plane of the Milky Way galaxy. If here's the center of the Milky Way galaxy, and the Pac-Man over here is where the Earth is, each contour is a contour of constant total summed up free electrons. So in other words, if you measure a certain dispersion in some direction, you just look at the map and you say, if you measure 200 in whatever units, you know it's this far away. Or if you look in this direction, you measure 600, you know it's this far, a source is this far away. So in any direction in the Milky Way galaxy, we have these kind of models that tell us how much dispersion you could possibly have. And this is a two-dimensional model I'm showing here through the plane, but it's a three-dimensional model. You could look there, you could look there, you could look there. And in particular, I can tell you from the model what the maximum total amount of plasma, total number of free electrons there are in any direction. And so that's what made Lorimer and his colleagues' jaw drop when they saw the degree of dispersion, the fact that it took this 300 milliseconds for this event to arrive. The high frequencies, the bluish radio waves arrived first, and the low frequency radio waves arrived several hundred milliseconds later. That implied, we call it the amount of dispersion, or the dispersion measure. The burst had this amount of dispersion. Don't worry about the units. This amount of dispersion, whereas our models of the Milky Way said the maximum you could have in that direction is more than 10 times less. There's 10 times more dispersion than you could possibly have. And they looked at the plot and they said that's impossible. It has to, or not impossible to be in the galaxy. It has to be way, way outside the galaxy. And to amass this amount of dispersion outside the galaxy, the space between galaxies, it's not a total vacuum, but it's way closer than in the Milky Way. You have to travel really far to encounter that many electrons to cause that degree of dispersion. So it had to be, they knew it had to be at or they inferred it had to be at a cosmological distance. And if an object is so far away, is billions of light years away, and yet we can detect it, it has to be a very powerful explosion. It has to be, in radio astronomy, the most powerful explosion ever seen. So this was detected at the Parkes telescope, and the Parkes observers were, pretty excited by this, and they started noticing there were quite a few of these events going off when they were started to be able to collect the data fast enough. And then they found that there was a class of these fast radio bursts that had kind of strange frequency sweeps, like this one over here. You see it was detected 2015. And it was sort of blobby and had kind of strange streaks. It wasn't like all the others that they were seeing. It was sort of curious. And they made a plot. In this plot, this is time of day in the Australian Eastern Standard Time. This is time of day. And the gray ones, the ones colored in gray, those are the ones with the weird frequency sweeps. And the dark gray ones, those are the ones that looked, pretty steady across the radio frequency band. And they noticed something curious, that, the light gray ones occur most likely at lunchtime. And the cosmos ought not to know when it's lunchtime in Australia. This just doesn't seem likely. And so that tipped them off that this was, something probably locally generated. And they started looking around what could cause it. They realized, there's a microwave oven in a kitchen not too far from the telescope, the visitors' quarters, where you heat up your lunch. And a graduate student went and stood there and opened it and closed it. And it turned out that it would cause a fast radio burst if someone was really impatient and they opened the microwave oven door before the microwave stopped. It's humming along, and then you just open the door, and the telescope had to be pointed in that direction. So it didn't always happen, but it happened often enough. And so they realized that this was not cosmic, and those strange frequency sweep events were caused by a microwave oven at the Parkes telescope. And science is wonderful. Science is wonderful because we publish. We are not shy, we're not embarrassed to say that if we make a mistake, and when we understand it, and you can see, they called the weird sources, I should have told you, they called the weird sources peritons, this Greek mythology thing, but in any case, what you can see in the abstract here, it says, subsequent tests reveal that a periton, this weird frequency sweep, can be generated at 1.4 gigahertz when a microwave oven door is opened prematurely and the telescope's at the appropriate relative angle. You have to understand, this is the monthly notices of the Royal Astronomical Society, one of the most prestigious astrophysical journals that exists. And they published it. Isn't science great? But to me, what's amazing, it says this and other distinct observational differences show that FRBs, the ones that don't care about whether or not it's lunchtime, the ones that occur randomly in the day, those they concluded are genuine extragalactic transients, and indeed they were correct. And so you might say, okay, they're real, so what are they? And there was a whole host of possible models for what FRBs are. In fact, for a while there were way more models than there were observed events. That was kind of a weird situation. Exploding stars, colliding neutron stars. Could they be a neutron star hitting a black hole, asteroid, all sorts of ideas. One of the models that was suggested was that they're magnetars. Magnetar sounds like a really cool object. Magnetars are highly, highly magnetized neutron stars. Something I actually studied quite a bit for many years. These are stars where the magnetic field is, it's the highest magnetic field we know of in the universe, and it's so strong that it sometimes is unstable and causes huge explosions of X-rays and gamma rays, and these are observed. So this is observed, I wouldn't say ubiquitously, it's fairly rare in the galaxy. But these have been observed, and with X-ray telescopes, gamma ray telescopes, but not so much radio telescopes. So here we know there's an object that can explode and explodes with millisecond bursts, but has only been known in the X-rays, not known for radio bursts. But still, there were arguments that it could be a magnetar, and I'm going to come back to this point. Now you might wonder, okay, if you think it's at a cosmological distance, why don't you just look with an optical telescope, see what galaxy it came from and where in the galaxy it came from. And so magnetars, these are very young objects, so you should see it, in a region where stars are forming or in a young galaxy. And if you look and you see it in an older galaxy, it's probably not a young object like a magnetar. And so you might say, why don't you just go and look where it came from? And the problem is that radio telescopes, particularly single radio telescopes like the Parkes telescope in Australia, we call it the angular resolution, or when you see a fast radio burst, the region for which you can pin on the sky that you can pinpoint the burst came from is pretty large. Just the property of radio telescopes, they have pretty blurry vision, very blurry vision. So you think, oh, it came from right around there, but right around there has 1,000 galaxies. So it's impossible to know which galaxy it came from. And it turns out that the ability to pinpoint gets better as you make the telescope larger. And so there was a large radio telescope called the Arecibo telescope. I'm going to show you pictures shortly. Even if you went, and this at the time was the largest radio telescope ever built. And even today, the 500-meter FAST telescope in China, still there would be hundreds of galaxies in the localization, in the uncertainty region from where the object came from. It's just too big, you can't tell. Now, there's something called the Very Large Array, a different kind of radio telescope, an interferometric radio telescope. I'm going to show you a picture shortly, that if you could, that it can pinpoint really, really well. But the problem is that it doesn't have a big field of view. So even though it can tell you it came from exactly there, it can only look exactly there. And the chances of detecting a transient source, you don't know where or when it's going to happen, are tiny. So it's hopeless to detect them, or seemingly hopeless to detect them with an interferometer. But then, now, up until a certain point, only the Parkes radio telescope had detected any of these, and the Parkes people were kind of nervous. Like, what if it's a mistake? Like, what if it's not the microwave oven, but it's something else locally? And they said to other astronomers, have you seen one by any chance? And we were all looking, and in particular, me and my group were looking using this radio telescope, the Arecibo Observatory in Puerto Rico. This is a 300-meter aperture. It no longer exists. Sadly, it was destroyed accidentally. Well, not really accidentally. There were problems, some technical problems with it. Anyway, we don't have to talk about that. But in any case, this is the 300-meter aperture. This here is a three-story large visitor center. It's a fantastic museum where school kids from Puerto Rico could come and learn science. A giant parking lot. This here is a catwalk. This you can go out and walk on that catwalk. It's scary. It's pretty scary. It's hundreds of feet. In fact, this is me on the catwalk at Arecibo at the top. I'm right here. Up here, if you zoom into my knuckles are white. It's really scary up there. There's a couple of colleagues of mine, Paul Ray and Maura McLaughlin, who I believe Maura is coming here next week. In any case, we were looking for fast radio bursts. We finally found one, and we were so excited. We found one. We called the Parkes people. You found one? Yes, it's real. And here is the first fast radio burst that our team found at the Arecibo Observatory. And you can see here's time. Again, a few hundredths of a second total, and radio frequency. And you see the telltale dispersive sweep, which you can correct for, and here's the burst. It's kind of a puny burst, but it was definitely real. We got very, very excited. But to our amazement, we kept staring in that position on the sky, and it repeated. And that was a real moment, because none of the Parkes bursts, they kept staring. Parkes kept looking at their burst. They had never seen it happen again. This one, we actually looked for months, and I had a grad student who kept analyzing the data. It was getting kind of boring. Do I have to? Is it boring? And I was like, yeah, I guess you should. And then he'd look at more data, didn't see anything. And I was starting to get bored. It was like, okay, I guess they don't repeat. And then one day, he was particularly diligent, this student, and he kept analyzing all the Arecibo data we were getting. And one day, in an hour, he saw 10 bursts. 10 bursts at the same dispersion measure. Now here in software, we've corrected the dispersive effect. We've removed it just for the eye so that you could see certain features. But they're all dispersed exactly the same way. The amount of plasma this source has come through is the same for every burst, which makes sense if the source is fixed. And you see all these bursts happened in about a span of an hour after 6 months of looking and not seeing anything. And well, before I tell you about that, I'll just say, just look how different they are. We were just blown away. There's some that were incredibly bright. Look how bright that is. Some really dim. And some were incredibly bright at the bottom part, the lowest radio frequencies, and some are incredibly bright at the highest radio frequencies. These two are just 6 seconds apart. That sort of change of what we call spectrum, the amount of radio frequency, the amount of light you have at the different frequencies, that's unheard of. We've never seen a source do that before. We were just blown away. We got a lot of press. There's Paul Schultz, who is the grad student who made this discovery. And you see the cosmic hunt for fast radio bursts just got a surprising new twist. They can repeat. And it was so exciting because, instantly you knew that this is not some star that explodes. A star can't explode, cataclysmic explosion. It can't have blown itself to bits, or like a supernova explosion. It has to be something that can happen over and over and over again. And that eliminated in one swoop, at least for this source, a whole class of models. And it was just so exciting. It was exciting in terms of understanding what the source was, but exciting for another reason, because now you knew where you could point. And if you were patient enough with your interferometer that can localize on the sky really well and eventually find the galaxy, so you could then figure out what galaxy it came from. And we got so excited. So we went and we called up the director of the Jansky Very Large Array in New Mexico. Each of these is a very large radio telescope, and they form an interferometer operating in tandem, able to localize. And we hoped we would detect a burst from this direction because it repeats. And of course, the source doesn't cooperate. You get this time and you stare at nothing, and you wait, a month. You get a few hours at a time. It's all you get on the VLA. Everybody wants to use. All astronomers want to use it. So we went and we saw nothing, and then we went back and we saw nothing. And then we asked, "Would you let us look a third time?" And they were getting a little skeptical. We said, "Really?" And they said, "Okay, one last time." So we observed for 60 hours on the VLA, which is a long time. And we saw no bursts, and they were getting kind of fed up with us. But finally, in the third set of observations, the source finally cooperated. It was so gratifying. And this is a plot on the sky. The black circles are where we knew somewhere it had to be in those circles. That's the uncertainty region from the Arecibo telescope. And for arcane reasons, the VLA gives you this sort of cross pattern, and this is the dots we knew, that's where the source has to be. And in fact, in that observation, not only did we see one, we saw 6 more bursts, all from the same position, and importantly, all with the exact same dispersion measure as what we saw from Arecibo. So we knew it was the same source, same part on the sky, and repeating again. And then we had it. We nailed the position to enough. I said 9 bursts in 2016, caught with the Very Large Array. That let us propose, for time. So you see how this works. Like you go and you get the position with the VLA, and then you call up the director of this telescope, the Gemini telescope in Hawaii, and you say, "Oh, we have this incredible source," and they say, "Yes, you can have the time." And we said we were expecting to find a big, beautiful spiral galaxy, and instead we found, so this is the Arecibo uncertainty region. This is where we knew it had to be from the VLA. And in that space, it's not a big, beautiful spiral galaxy. It's this puny little dwarf galaxy. And we were just shocked. Again, we were not what we expected at all. Why a dwarf galaxy? And so we're wondering what kind of sources exist in dwarf galaxies. And it was really a new puzzle. But the good news was that this whole story I told you about dispersion and the amount of plasma that it had to go through was probably at cosmological distance. It was all correct. Because when you find the galaxy, you can then measure directly what its distance is. And that's using, we call it the redshift of the galaxy and optical spectrum. But never mind, we confirmed that indeed this event had come from a cosmological distance. This was the first true proof that these fast radio bursts were coming from billions of light years away. And then we got lots of press. That was really exciting. And here, the very famous New York Times science writer Dennis Overby, some of you might have written, he wrote, "Fast radio burst traced to faraway galaxy, but the caller is probably ordinary physics." And I have to say I didn't like that headline very much, because then I thought, I should go to his house late at night and explode one and see how ordinary he finds that. But never mind that, because, New York Post. It's like we never said that. We never said that. We don't think that. I don't know where they got that, but there you go. Interesting contrast right there. Anyway, so this was all just in 2018, something like that, or around 2019. Where did we stand? We knew at least one FRB repeats. We had ruled out exploding or colliding stars. You can't, in neutron stars, if you have a pair of neutron stars like I showed you in that movie, they collide once. They're not going to collide 6 months later, 10 times in an hour. It just didn't make sense. And it had enabled the first localization and galaxy identification. But there were still so many open questions, like, do many or all FRBs repeat? If you just wait long enough, is it eventually going to repeat? What is the bursting source, and why is it in that tiny, puny galaxy? We had a million questions. And we knew we needed to find more, but we knew we needed to find more to answer these questions, but also for a different reason. And the different reason is because when I show you cosmological distances, and I show you, galaxies and galaxy clusters, the truth is that there's matter distributed everywhere throughout that universe in a very interesting, complicated way that arises from the expansion of the universe following the Big Bang. How matter is distributed in the universe is actually an interesting open question, and something that even if we never understand the nature of fast radio bursts, what is remarkable about them is that they give us a novel probe of the matter distribution in the universe. So even if we never understand them, by having them all over the sky, if you have enough of them, the radio waves interact with matter as they travel. You can see, if you know how far they are away and you see how much plasma, that's telling you about the matter distribution in the universe, something we've never been able to measure in this way before. Not the free electrons, we've never been able to do before. It's a new way to study matter in the universe. So we knew, but you need a lot of them to do this. You need them all over the sky. How can you do that? And so now I'm going to tell you about this wonderful telescope that we've built in Canada. How much time do I have left? How much time do I have left? Okay. You don't know how much I have to come, so how do you know I'm fine? But okay, the Canadian Hydrogen Intensity Mapping Experiment. And notice the word FRB doesn't occur in the title. Hydrogen mapping, what does that have to do? It has nothing to do with it. It turns out this telescope was designed for totally different purposes, for a cosmology experiment that I'm not part of. But this is the telescope in British Columbia. It doesn't look like a telescope, does it? It looks strange, but it is a telescope. It's a radio telescope. These are cylinders. Each cylinder here is 100 meters long, 100 meters by 20 meters across. So the total collecting area in Canadian units is about 5 hockey arenas. I'm a hockey fan, so. There's no moving parts in this telescope. It just stares directly overhead. The cylinders are oriented exactly north-south. So the sky rotates from east to west every day, and we cover the full northern sky every single day in the frequency range of 400 to 800 megahertz. And so the way this works is there's 256 antennas hanging on the axis of each of these cylinders, the radio waves come in from outer space, bounce off the surface of the dish and into these antennas. The total input data rate here is 13 terabits a second into these antennas. Sorry, I should say that just like in the radio, the antennas collect the radio waves by producing currents in them that then get sent down to circuitry and amplifiers and digitizers that exist in these shipping containers that are right next here. And like I say, the total input data rate that gets digitized is 13 terabits per second. That's comparable to the world's entire cellular network. And it's all being analyzed in real time on the site, thanks to supercomputers that are sitting also in those shipping containers. And there you can, just for scale, that's the FRB team standing in the axis of one of the cylinders. And the way this works is that there's these 4 cylinders that the signals go into different components of electronics that I won't tell you about. But if you're really curious, come tomorrow. I'm giving another talk with more details. And we actually do hydrogen mapping and some pulsar timing at the same time as we search for fast radio bursts. 24/7. It's always operating autonomously. Yeah, and you can see where all the electronics is housed. And this is really a student-run project. These are students, my PhD students, my colleagues at University of Toronto, University of British Columbia, elsewhere. You can see this was all put together as me and one of my PhD students. We just screwed in 10,000 cables. That was really fun. It actually was fun. But anyway, now why cylinders? Why would we do cylinders? So, you know, a conventional radio telescope, the parabolic Parkes radio telescope, it sees a tiny little portion of the sky, as I was describing, but for a phenomenon that is all over the sky and you can't predict where, when it's going to happen, it's going to miss most of them. It just can't see them all. But a cylinder, it only focuses in one dimension. It sees a huge swath of the sky at the same time. And so it's much more efficient than we say the field of view, the instantaneous field of view of the CHIME telescope compared to the Parkes telescope. It's a different ball game. It's a different ball game. And so then, you know, when these flashes occur, as they will, there we go, we just collect more of them. We collect orders of magnitude more because of the geometry of our dishes. And so here, when we started detecting fast radio bursts, there we are on the cover of Nature, Space, and CHIME, very clever. And this is a histogram of the number of fast radio bursts that were detected before CHIME turned on. And you can see Parkes was doing quite a good job. And then there's a new Australian telescope called ASCAP that was doing pretty well as well. And then when CHIME turned on, you see, different. I'm Canadian. I'm trying to be humble, but we're seeing. Look at that. Sorry, and you see, this is now 2019. But this event rate has continued, and it's really very much. We have thousands of FRBs now. There used to be there were just a handful. Now with CHIME, there's thousands, and we can study all sorts of interesting things about them. One thing, we've now cleaned up in repeaters. This slide says 20. It's actually 50, and we probably have another 50 that we haven't published yet. The CHIME sees the sky every single day, the entire sky every single day. So we clean up. There's lots of repeaters out there, not just the one that Arecibo saw. There are many, many new repeaters. This is just a sample of them. The green one, their color, this clever student of mine figured out how to display this. The ones in the same color are the same source. And what's curious is we've discovered that because you have lots of statistics, when you get statistics, you can find all sorts of stuff. So the repeaters, they tend to have slightly different burst shapes than do non-repeaters, or at least apparent non-repeaters, because one day they could repeat. But if you just split them by repeaters and non-repeaters, the repeaters have weird morphologies. We don't know why. And then one day we detected, this was just after the COVID lockdown, so we were all kind of, gee, what do we do now? And we knew what we were going to do, because suddenly there was an enormous burst. It's not so clear how enormous it was, but it lit up the entire CHIME telescope. Almost the full field of view saw this. This was a huge, incredibly luminous radio burst from a source in our own galaxy, from a known magnetar. So, before when I was telling you about the different ideas for what fast radio bursts could be, and I told you, well, I mentioned magnetars because we later detected one. And this was a big shock. Wow, if you detect a magnetar in the Milky Way, does that mean all FRBs are magnetars? Is that the answer? No, not so quick. That's not the truth. So this is a bit of a more technical slide, so forgive me, but what I'm showing here is distance on the x-axis. So this is a huge, so now almost in light years, so this is 1 billion light years, 10 to the 9 is 1 billion. It's not quite light years, but it's like light years. And this is, 1,000 light years. These are all galactic sources, and this is, by the way, how bright the source is. This is how bright it is. So these are galactic sources. These are the fast radio bursts. And these are lines of constant energy. It's a little technical, I'm sorry, but these are lines of constant energy. The main point is this new source that we detected in the galaxy was by far the most luminous radio source we'd ever seen in the galaxy. And it is hinting, I'm running out of time, I can tell. It's hinting, it has roughly the same energy as the least energetic fast radio burst. That's what I'm trying to show. It's on this line here that nicks the bottom of these fast radio bursts over here. And the main point, if the plot's not clear, don't worry. What I'm trying to say is, if you took this galactic magnetar and you put it in another galaxy nearby, it would look just like a fast radio burst. But it is way less bright than the brightest, like many billions of times less bright than the brightest fast radio burst. So we don't really know they're all magnetars. In fact, most of them might not be magnetars, but at least some are almost certainly magnetars. Yeah, so that's what it's like to work in CHIME, where we have tons of data. We've published our first major catalog of 500 sources, working on our second catalog with 4,000 sources. And by the way, if you want to see what we're detecting, you can subscribe online, go to this website, and you can get in your email each time we detect a fast radio burst. You probably don't want that, and we have lots more coming. And I'll just mention, because I'm here in California, the CHIME telescope, it detects, like I say, thousands of these bursts, but the weakness is that CHIME alone cannot determine what galaxy they came from. The angular resolution is not so great for CHIME, but we have a plan. We're going to fix that. So what we're building are mini CHIME telescopes. We call them outrigger telescopes. And we're going to form an interferometer. We're creating our own interferometer just for fast radio bursts. We've already built one not too far from CHIME. It was our first one. We're learning how to do this. But it's built. Nope. So there it is. You can see it's built and operating. 40 meters, just one cylinder. And we've built a second one in Green Bank, West Virginia, on the other side of the continent, because we want to be able to pinpoint. They're all going to watch the same positions they're all going to watch this CHIME sky. CHIME will detect it and then send a signal. They're going to buffer data, and then when CHIME says, we saw one, they're going to dump it, and then we're going to do this interferometry. And so the second one in West Virginia, there it is, it's built, and if you look carefully, it's a US flag and a Canadian flag, I like that. And the third one will be built here in Northern California, in Hat Creek, on the grounds of the SETI Institute in Hat Creek, California. And let's see, I didn't. So if you come tomorrow to the talk, I'll show you some pictures of us digging the foundations to build the telescope. But we expect the first light of this interferometric array that will allow us to pinpoint every single chime-detected fast radio burst on the sky, hopefully by the end of 2024. And so in summary, they're mysterious. Some might be magnetars, but we don't know if all are. Some repeat, but we don't know if they all repeat, and there could be multiple classes of objects. And CHIME in Canada, and now in the States too, is helping to solve this mystery. And no matter what, even if we never figure out what they are, they will be fantastic probes of the universe. And I'm going to talk more about that in the physics colloquium tomorrow. And I say stay tuned, and thank you for your attention.
Well, thank you very much, Vicki, for that great talk.
And I'm just leaving you with a drone view of CHIME.
Okay. We do have time for a few questions if you'd like to ask Vicki, so let's go ahead and take a few questions from the audience. You can raise your hand, I'll point you out. How this gentleman here first?
Yeah, the initial observations showed the burst at 1.4 gigahertz. Did you decide to build your telescope from 400 to 800? How did you make that?
Yeah. Great question. So it was designed for a different experiment. It was designed for mapping highly redshifted neutral hydrogen. So neutral hydrogen gas produces radio waves at 1.4 gigahertz. And if it's redshifted because the universe is expanding and you want to see in a certain redshift range, you go to lower radio frequencies. So 400 to 800 was chosen by the cosmologists. And it was a risk. So because we had to change all of their electronics, because in cosmology you don't need millisecond timescales. We needed millisecond timescales, and so we went to them and say, we'd like to do this, but it was risky. We didn't know we would detect any FRBs in the CHIME range, but they're there. Yeah.
And gratifyingly, you can do cosmology with them. So
Yeah.
there you go.
Yeah.
Other questions from the audience? Gentleman over on the right.
Is there any interaction between the FRBs in your search here and dark matter?
Oh, and dark matter. That's actually a really interesting question. So some models for dark matter posit that it's macroscopic, that it's not just particulate, and you could have, for example, black holes could form part of dark matter, and we've done experiments looking for that, but there's certain ranges of black hole masses that the experiments we've done don't constrain. And so there are ideas, and there's theoretical papers that have been published suggesting that if you had enough of the dark matter in black holes, that eventually some fast radio bursts would get gravitationally lensed, meaning you'd see multiple images. So you'd see a burst and then another identical burst not too long after. And so the CHIME data set is actually fantastic for searching exactly for that. And we have done those searches, and we have not yet detected any gravitationally lensed FRBs, and that actually allowed us to set an interesting limit on the fraction of the dark matter in a certain type of black hole called a primordial black hole. So there could be that interaction, but we have yet to see it, and we're going to keep looking. Yeah, it would be awesome if it would be so cool. Yeah.
I was curious about when you were talking about making this 3D map of the matter in the universe from the dispersion measures and from the FRBs. It also sounded to me like the dispersion measures themselves were also a proxy for distance in their own way, I guess.
Yes.
So is there that correlation there, or are you using outside information, maybe the galaxy itself or the properties of the galaxy?
Yeah. So this is actually what I'm going to focus on a little bit more in the talk tomorrow. But you're hitting the nail on the head. Okay, how does this work? So the problem is that the dispersion measure is the sum total. It's the integral of all the electrons. And so you get some in our galaxy, which we think we can model out. You get some in the intergalactic medium. You get some in the host galaxy. And you have to try and estimate how much you get there. And if you can't see what the host is, and you don't know if it's an edge-on spiral galaxy or face-on spiral galaxy, it's a huge difference in contribution. And then on top of it, if you travel through the cosmic web at a cosmological distance, you're going to nick the halos of many galaxies. And each one of those has some, we believe the Milky Way and all galaxies have a halo of free electrons around them. So you're going to hit them at different distances, different impact parameters, and that will contribute to all of that dispersion. So it's really a statistical game that you have to play, and it helps tremendously to know the redshift where it started, so to have identified that galaxy. So this kind of science, so there's that. But that's not, so I haven't told you the whole story, because it's only an hour, and I probably went over my hour. Radio waves not only get dispersed, they also get scattered. And so some fast radio bursts, we detect scattering. That has to do not just with the total integral of the free electrons, but also how they're distributed if they're turbulent. If those free electrons are in blobs that are moving around, that causes scattering of radio waves that we can measure also. So FRBs give us also a scattering measure that tells us not only about the matter distribution, but also how the matter is clumped, how it moves. But that's not all. It's like there's more to it than just that. They also scintillate. You get scintillation, and also we can measure magnetic fields. So FRBs, I didn't tell you this, are hugely polarized. You can detect magnetic fields using that. So we can detect the distribution of magnetic fields in the universe. There's tons. I said matter distribution. It's more than just that, actually.
Yeah, what is the main systematic error time-space when detecting FRBs?
So say it again?
Systematic errors in time while detecting FRBs.
What are the systematic errors? Oh yeah, there's lots. So I don't know where to start with that. I mean, there's like, where do I start? So let's say you want to know how bright the FRB was. Like, that's a basic thing. When you publish a paper, you like to say where the source on the sky is pretty basic. Where is it on the sky? That's hard for us to do. We can say over there. We can give a large error region. And how bright was it? That's really hard to do also, because if you don't know exactly where it is, the sensitivity of the radio telescope is a very strong, so radio telescopes, they have sensitivity, even, here's CHIME, and that's overhead. It's actually a little bit sensitive over here and here and here and here and here. We call that side lobes of the radio telescope. And so an incredibly bright source in a side lobe looks like a faint source overhead. It's a big problem. And so it's a huge systematic effect when we want to report the fluxes, how bright an event is. That's one of the other problems that we have. But there's others.
Great. Let's go. Jack?
I'm just curious, how many FRBs have radio polarization measurements? And I'm excited to learn about that. What does that tell you?
Yeah. So with CHIME, the way that the telescope works, it's a trigger-based telescope, and when we detect an event that's bright enough, we save buffered data. And there's two types of data that we can save. And one type is not sensitive to the polarization, and that's the small version, that's like a compact version of the data that's easy to save. And then for events we really, really love, then we're going to dump all the data, and then we call that the raw voltage data, which is basically the raw voltages from every single one of the 1,024 antennas. Actually, 1,024 antennas, each of which has two polarizations, so it's 2048 signals, very voluminous data set. And so we've done that. We just published a paper with polarization results for 140 FRBs, but we're sitting on another 2,000. It takes this slow to process. And so most of them are polarized to some level. Some of them are 100% linearly polarized. Some are a little bit circularly polarized. There's a very interesting phenomenology that I'd love to share, but
Got a few more questions. Let's have one way in the back there.
Yeah, so you mentioned two fast radio bursts
that were associated with actual things you could see in the sky, how many radio bursts have been associated with the meteor?
Yeah. So very good. So the ASCAP telescope in Australia, I didn't show that telescope to you, but it is an interferometer that has, they have built the antennas at the focus of their dishes so that they can simultaneously see an interesting area of the sky, not as big as CHIME, but still pretty big, and they can localize at the same time. So they'll detect, a couple dozen events per year, but each one of them, they can determine what galaxy it came from. So there are a couple dozen of sources where the galaxy has been seen, has been identified. A couple dozen. There's probably more they haven't published, and because it takes time to publish.
Question up front here.
How do you intend to fix the flux problem from the questions?
Great question, yeah. So the problem with the flux is, this is kind of technical, but that's awesome. I love that. So when you don't know exactly where it comes from, so like I said, there's two different types of data. There's the data that is, we've thrown away the polarization, and we've just, it's a little technical. So yeah, I'm not going to be able to explain this really quickly, but
at the end afterwards.
Yeah, I think it's better at the end. The bottom line is that we have the data that will allow us to digitally beamform after the fact for the brightest events. And then once we know where it is on the sky, then we know how sensitive the telescope was to that region, and then we can determine the flux much better. So with the outriggers, we're going to do a good job.
I think you've had your hand up for a while, so let's...
Yeah. Is there any evidence that these events, whatever they are, they have signatures in other parts of the spectrum?
Oh, yeah. So we would love to know that. That would be awesome. And we've looked. So there's one FRB. I didn't have time to talk about it, but the closest FRB is in a nearby galaxy, the M81 galaxy, a Messier, a very bright, very nearby galaxy, just a few megaparsecs away. And so that's that's a repeater. And it's a prolific repeater. It's always bursting. And so we have gone and stared at it. The most theoretical arguments suggest that X-rays are the best place to look, especially if they're magnetars. I told you, if they're magnetars, we know magnetars produce lots of X-ray bursts. So we've gone and we've gotten time on X-ray telescopes, and we've stared at it quite a bit. It's actually a postdoc at McGill, Aaron Perlman, who's done this work. And he has not detected any X-ray bursts, even though we've sometimes, and this is not easy to do, we got the X-ray telescope to look at the same time as a ground-based radio telescope and detected bursts during that time with the radio telescope, and we see nothing with the X-ray telescope. So I can't say that for sure there's no X-rays, but we have yet to detect any from an FRB.
Let's take maybe a couple more general questions, and then maybe we can have some private discussion at the end. Any last pressing questions? One gentleman here.
Could you give us an overview of the cost of running a project like this? Is it power to drive the computers, or is it grad students?
Okay, you want the budget breakdown? Sure. The telescope itself cost the structure itself was because there's no moving parts. It's not that expensive. So it was $10 million, something like that. Small, like by astrophysical standards, it's nothing. Then we had to upgrade it with better computers, better backend, and the whole correlator had to be redesigned if we want to do the fast transient science. The total was around 16 million Canadian dollars just for the hardware. And then everything else, we had some very small number of professional staff, and the rest is graduate student postdoc run. The power consumption, you're right, the power is the biggest consumable right now. It costs us about $180,000 a year. Oh, these are all Canadian dollars. So, divide by whatever, it's about 3/4 of that in US dollars. So 180,000 Canadian dollars for power per year. And then there's the grad student, then the people costs. So it's not that expensive. So the total operating cost is just about 2 million Canadian dollars a year for all the staff and the electricity, parts, warranties.
How much is one of those shipping containers full of CPUs?
How much does the shipping container cost? Oh, I don't know. It's probably $10,000 or something like that. I don't know, maybe not even. Yeah, it's $5,000, something like that.
With the computers?
Oh, with the computers, yeah. So the FRB machine has 128 CPUs, but they're 5-year-old CPUs. In fact, we're planning to upgrade all of this, but probably with 128 CPUs that are 5 years old, we can now do it on like 10 computers today at a tiny fraction of the electricity cost. So I'm really keen to upgrade this thing. The correlator is currently 256 GPUs, so that was a little more expensive. So I don't know, what is that? Probably $1 million or something like that.
Well, with that thought about potential bigger and better coming, let's all thank Vicki again. Thank you all for coming, and we hope to see you next year at next year's Bunyan.